Good morning to all. Today we will continue with the topic of process scheduling algorithm. So, in the last lecture, we have seen popular three process scheduling algorithms. So, we'll quickly revise what we have seen. Then we can take the discussion further. So, process scheduling refers to the policy of deciding that which process will be scheduled next among the ready processes, and depending on various factors, certain policies are defined in order to schedule a new process from the set of ready processes. So we have seen one technique or one algorithm, that is FCFS, that is first come first serve. So in first come first serve, you simply put all the new processes in the ready queue, and whichever process came first, that process will be executed first, and whichever process came last, it will be executed last. So it will follow simple queue mechanism. And the important thing is that here the decision mode is non-preemptive. The meaning of non-preemptive is that once you start some process, it has to complete. Once some process is started, it has to complete. You cannot terminate it in between, right? You cannot terminate it in between. So that is the meaning of FCFS. So FCFS is overall a good scheduling policy. It has certain disadvantages. Disadvantage is that if a long process is coming, and immediately after the long process there is a short process, so that short process has to wait for long time because of the previously active long process. That is one of the disadvantage, and this disadvantage is caused because of the non-preemptive nature of the algorithm. Second technique which we have seen is round robin. So in case of round robin, it is a preemptive technique, and each process is assigned a fixed time slice, a time period for which it can execute maximum. So if you are defining time period 1, for example, then each process can execute only for one time unit. After that, it has to switch. So in this way, round robin will give fair chance to each process, and fair in the manner that every process will be executed for only same duration of time, that is your time slice. So one by one, the processes will get executed and they will switch. And this is the scenario of round robin. The disadvantage of round robin that we have seen was it sometimes favors the processor bound process, right? Because if the processor bound process takes the processor, then it will utilize a full time quantum, and IO bound processes will require only some portion of time quantum, and then it will go to the waiting loop. And when it comes back again, it will immediately go to waiting loop. So it is not able to utilize the processor properly, the IO bound processes. So this is a disadvantage. To solve that problem, we also introduced one modification in the round robin. It is called virtual round robin scheme. So in the virtual round robin scheme, as you can see, we have one ready queue, and in addition to that, we have multiple IO queues, IO1, IO2, and so on. And also we have auxiliary queue. So when the process is finish the IO operation, when the process finishes the IO operation, instead of going to the ready queue, it will enter the auxiliary queue. Instead of going into the ready queue, it will enter into the auxiliary queue, and between these two queues, ready queue and auxiliary queue, when a new process is to switch, when a new process is to start, the auxiliary queue will be given more priority compared to ready queue. What is the reason for this? The reason is that in ready queue, certainly there will be new processes which are coming into the system, or there are the processes which has not gone to the IO waiting. So these processes are there in uh, ready queue, whereas in auxiliary queue, the processes which are going to the IO waiting, they will be in the auxiliary queue, so they should be given more priority. That is why auxiliary queue is given more priority. So here you can kind of reduce the overhead, and IO waiting time you can reduce, and you can add some more fairness in the overall execution compared to the simple round robin. But again, if you add some new functionality, it will take some more overhead. So here you are introducing one more queue. To handle that queue, you require modification in the algorithm. Overall overhead will increase, but you can solve the disadvantage of the normal round robin by introducing auxiliary queue and virtual round robin. So that was round robin, and the next algorithm which we have seen was SJF, or shortest job first. So what is the purpose of shortest job first? Again, it is non-preemptive algorithm. So in the shortest job first, when a process comes, it will be executed till it finishes. When the currently running process finishes, when the currently running process finishes the execution, the processor will check among the already processes, and it will determine that which process has the shortest remaining time, right? A shortest job, I mean, which process has the shortest uh, CPU time, burst time, shortest execution time. So whichever process is shorter in nature, it will be executed, and in that way, shorter processes will execute faster, and whichever processes are lengthy, whichever processes have long CPU time, they will keep waiting. One of the disadvantage, the last thing which we discussed is one of the disadvantage of shortest job first is starvation. So what is the meaning of starvation? Starvation means when the currently running running process is executing on CPU, and because of that, the processes which are waiting in the queue, they will not get the chance to execute, and they will wait for infinite time period. That is called the starvation, and starvation happens in the SJF because it will always prefer the shorter execution time. It will always prefer the shorter execution time. So uh, if the process is longer in nature and shorter processes are keep coming, then the long process will never get the chance to execute. That is why it is called causing the starvation in some cases. So that is your SJF. Now the next algorithm which we have to see today uh, is this issue with SJF, the starvation. The next algorithm which we have to see today is SRT, or shortest remaining time. It is also sometimes called SRTN. It is also called SRTN sometimes. Shortest remaining time next. So what is the fundamental concept of SRTN? So the shortest remaining time policy is basically preemptive version of SJF. This preemptive version of SPN or SJF. So you already know the philosophy of SJF, every time you have to look at the ready processes, whichever process is short in nature, that you have to take. But in case of SRTN, see, in this case, the scheduler always chooses the process that has the shortest expected remaining process time, right? Shortest expected remaining process time. So it doesn't look only at the service time, it will look at the remaining time of the process, right? It will look at the remaining time of the process. So we will see with example. But what he says, when a new process joins the ready queue, it may have a shorter remaining time than the currently running process. So accordingly, the scheduler may preempt the currently running process when a new process becomes ready, right? For example, suppose process P1 is executing, okay, it has a execution time of 6, right? So it is executing from 0 to 5, right? So between 0 to 5, it is executing, but consider at time t equal to 2. Consider at time t equal to 2, there is a new process P2 whose CPU execution time is only 1 time unit. So what is the scenario? At time t equal to 2, process P1 has still 3 time units left. Process P1 has still 3 time units left, but process P2 has only 1 time unit left. So what it will do, it will preempt the process P1. It will preempt the process P1 and schedule the process P2 because P2 has the shortest remaining time compared to P1. Okay. So if you look at it in the other way, it simply means that every time when the new process joins the queue, every time when the new process joins the queue, you have to do the scheduling. You have to do the scheduling. And by scheduling, I mean that you have to look at the remaining times of all the remaining processes, and accordingly you have to choose the process with shorter remaining time. Okay. So when a new process joins the queue, you have to do the scheduling, and you have to look at the remaining time of the processes, and accordingly you'll preempt some process and schedule the another process. So that is SRTN. Now let's look at our example with SRTN. So if you remember, our processes were A, B, C, D, E. The arrival time was 0, 2, 4, 6, and 8. And the CPU time, means the service time, was 36452. Okay. Now here let's also add one more field, that is remaining time. Remaining time. So now if we put the Gantt chart, okay. So let's start the process. Obviously, at time t equal to 0, we are at time t equal to 0. So there is only one process, that is A. So A will execute from 0 to its service time is 3, but it will execute from 0 to 2 because at time t equal to 2, a new process is coming. So when a new process is coming, you have to stop and see the overall execution scenario and determine the remaining times and accordingly proceed, right? So let's execute A from 0 to 2. So if I execute A from 0 to 2, so out of 3, 2 units have already been executed. So remaining time is 1, right? remaining time is 1. So here remaining time is 1, and for B, which is a new process at time t equal to 2, its remaining time is still 6, right? Its remaining time is 6. So if we take decision between these two, obviously A has a shorter remaining time. A has a shorter remaining time. So A will complete the execution from 2 to 3, which is its remaining time slice. So A will finish the execution at 2 to 3. Now A's time is over. Now at time t equal to 3, if we see, there is only one process, that is process B. There is only one process, that is process B. So we'll take up process B. B will start executing from time t equal to 3. B will start execution from time t equal to 3, and it will execute for one time unit. Okay, why for one time unit? Because at time t equal to 4, new process is coming. At time t equal to 4, new process is coming to execute. So it will execute from 3 to 4, and its original CPU time was 6, but it has already executed for one time unit. So its remaining time is 5. Okay, its remaining time is 5, and a new process C is coming. What is the remaining time of C? The remaining time of C is 4, right? Remaining time of C is 4. So now, as per our policy, we have to look at the shortest remaining time, and between B and C, C has shortest remaining time. So C will be taken for the execution, and it will execute from 4 to 6. Why? Because at time t equal to 6, a new process is coming. So we will execute C. We will execute C from time 4 t equal to 4, and it will execute till time t equal to 6. So C's execution time was 4. Out of that, it has already executed 2 time units. So remaining time is 2. So C's remaining time is 2. Now we have three processes, B, C, and D. The remaining time of B is 5. Remaining time of C is 2. Remaining time of D is 5. Okay. So we have these two processes, B, D, and C. So again, if you select between these three, B, C, and D, the shortest remaining time will be of C. The shortest remaining time will be of C. So again, C will execute from 6 to 8. Again, C will execute from 6 to 8, because it is only 2 time units remaining, and also at time t equal to 8, a new process is coming. So at time t equal to 8, we have this scenario. Process B has waiting time of, remaining time of 5, D remaining time 5, and E has a remaining time of 2. So again, I have to select between 5, 5, and 2, right? I have to select between 5, 5, and 2. So obviously, which process will be selected? We will select E. I will select E and execute it. So E will execute from 8 to 10. E will execute from 8 to 10, and its execution will be completed. So E's execution is over. Now if you see, I have two processes which are there in the waiting, that is B, its remaining time is 5, and D, its remaining time is also 5, right? So you can see that now you have two processes. And the remaining time of B is 5, and remaining time of D is also 5. So both of them have same remaining time. So in this case, according to your policy, you can select any one process. Let's assume that I have a policy that I will select the process which came first, right? I will select the process which came first. So let's see. Yeah. So here also same principle is followed. So if you select B, B will execute from 10 to 15. B will execute from 10 to 15. Its execution time is over, and remaining process is D. So D will execute from 15 to 20. D will execute from 15 to 20. So in this way, the execution will happen. So you can see, now let's go to slides. This is the overall execution cycle of SRTN. So SRTN and SJF, let's compare. So in SJF, the turnaround time, average turnaround time is 7.60, and in SRTN, it is 7.20, right? In SRTN, it is 7.20, right? So you can see that SRTN gives slight better performance than the traditional SJF, but the switching overhead is more. In SJF, in SRTN, the switching overhead is more. What is the meaning of switching overhead? It means that whenever a new process joins the queue, whenever the new process joins the queue, every time you have to look at the ready queue and calculate the remaining times, right? So that calculation will take some time, that calculation will take some resources, and those resources are kept busy, and that is the meaning of overhead. When I say overhead, this is the meaning of maybe it is a time overhead, maybe it is a space overhead, but overall complexity of the algorithm will be more if you use SRTN. So note the difference between SJF and SRTN. They both are following the same pattern, means they will give priority to the short processes, but the nature is different. SJF is preemptive and SJF is non-preemptive and SRTN is preemptive. If I take the example of your supermarket, in the last lecture we have understood that analogy. So in case of SJF, what happens that when the billing person is free, he can choose that whichever customer has low number of items, less number of items, they can be scheduled first, right? That is SJF. What is the meaning of SRTN? In case of SRTN, you see a person is doing billing and he has 100 items in his cart. Okay, out of that, 50 items are already billed. When that billing is being done, the person sees that there is a next customer who has only 3 items. So he says that to the current person, he says that you wait, let me finish the other customer who has fewer items, and then I will come back to you. Are you getting? That is the example of preemption. So preemption in theory, it looks good, but so how will you feel if you are a customer with that 50 items? You will say that I was taken first, so I have to finish. You finish my billing and then take the next customer, right? But he says that if the next customer has fewer items, then I will take him. You have to wait. So you may feel that it's not fair in the context of this supermarket. You may feel that it's not fair. So always remember that whichever algorithm, whichever scheduling policy is preemptive in nature, whichever scheduling policy is preemptive in nature, it will always have some overhead. It will always have some overhead with it, right? And you have to deal with that overhead. Anyways, so with this, we move to our next scheduling algorithm, that is HRRN. It stands for highest response ratio next. Stands for highest response ratio next, right? So see, till now we have taken two kind of thought process in our mind. When we schedule a new process, when we schedule a new process, so scheduling a new process, we look at the two aspects. One aspect is that process with more waiting time, right? Process with more waiting time, right? It means that the process which came first, which came earlier, right? So we are looking at two aspects. One aspect is that whichever process is waiting for a long time, right? Whichever process is waiting for the long time, we have to schedule it. We have to schedule it. Why? Because it's fair in that way that whichever process is waiting for a long time, I have to, you know, uh, give chance to that process. That is my policy. Second aspect, which we think is short execution time. Short execution time, right? So second thought process is short execution time. So we look at the current available processes and we try to determine that whichever process has a shorter execution time, whichever process has shorter execution time, that process should be taken for the execution. Why? Because it is shorter in nature. So we just need to finish that execution. So there are two thought processes, and based on different thought process, you have different algorithms. Like in here, uh, you have FCFS policy, and based on the shorter execution time, you have SJF and SRTN policy, right? But each of them have their own advantages and disadvantages. So if you talk about scheduling algorithm which favors the more waiting time, then its disadvantage is that it may prioritize the CPU bound processes. It may not work in fair manner to the IO bound processes. Whereas in case of short execution time, if you look at the SJF or SRTM kind of algorithm, they may result into starvation, right? They may result into starvation. So the HRRN policy, which we are going to see now, highest response ratio next. This policy, it kind of gives mixture of both of these thought processes. If you mix both of these thought processes, then you come up with the policy HRRN, which is highest response ratio next, which is highest response ratio next. Someone's mic is turned on. Please check and turn it off. So HRRN, highest, highest response ratio next. Let's continue. So first, let's define what is highest response ratio. Highest we already know. We have to define response ratio. So response ratio R is equal to W plus S divided by S, right? W plus S divided by S, where W is time spent waiting for the processor. W is time spent waiting for the processor. S is the expected service time, right? S is the expected service time, and R is what? It is a response ratio, right? So let's look at this ratio and try to understand its behavior. So waiting time means the time for which the process is waiting. So what is the meaning of that? Suppose process A, it arrives at time t equal to 0, and service time its service time is 10, okay, and current time is uh, let's say 5, right? So what is response ratio? So response ratio is, see, process A arrived at time t equal to 0. Process A arrived at time t equal to 0, but current time is 5. So it has not got executed. It is still waiting. Let's assume that it is still waiting due to some other reason, uh, due to some other process which is being executed. The processor is busy, and that is why this process is still waiting. So what is the waiting time? Waiting time is 5. Service time is what? 10 divided by the service time, that is 10. So its response ratio is 15 by 10, that is 1.5. 1.5. Okay. In the ideal case, let's take an ideal case. So in the ideal case, what is the meaning of ideal case? It means waiting time is 0, right? Ideal case means waiting time is 0. It means that as soon as the process arrived, in the system, it was executed, right? As soon as the process arrived, it got executed. So if the waiting time is 0, then the response ratio, so ideal case implies that waiting time is 0. So response ratio is what? It is S by S, that is 1. So in case of ideal scenario, the response ratio will be 1, right? This is the maximum value of the response ratio. Okay, sorry, minimum value of the response ratio. So this philosophy, uh, this philosophy of highest response ratio, logically, it does what? That we have to understand. So when I say response ratio is more, it means that waiting time is more, right? The nominator part should be more. In order to maximize the ratio, the waiting time should be more and the service time should be less, right? Because if denominator is less, then overall R will increase, right? The very simple maths here. So you can see that if we look at the process with highest response ratio, if we look at the process with highest response ratio, it means that that process is waiting for the long time because the waiting time is more. That process is waiting for the long time. Also, it has a less service time. So basically, both of these aspects are satisfied. Both of these aspects are satisfied. means that the process is waiting for the long time, and also its service time is less, right? Its service time is less. So this is the overall nature of HRRN, or highest response ratio next. It kind of gives priority to both aspects, waiting time as well as service time. So when the current process completes or is blocked, we have to choose the ready processes with the greatest value of response ratio. Greatest value of response ratio. And from this first sentence, you can see what is the first sentence, that when the current process is completed or blocked, right? When the current process is completed or blocked. So it means that the nature of this process, the nature of this policy is non-preemptive. Because it activates, this policy activates only when the currently running process completes, right? Only when the currently running process completes, it will get activated, right? So I think this is this should be very clear that its response, its mode of execution is non-preemptive. Mode of execution is non-preemptive. Okay, so let's look at its implications. So this approach is attractive because it takes care the age of the process. It takes care the age of the process. While the shorter jobs are favored, while the shorter jobs are favored, the aging without service increases the ratio, so that a longer process will eventually get past completing shorter jobs, right? It means that if the process is waiting for the long time, it will be definitely given priority. And also the process which is shorter in nature, they will also be getting the priority. So it is solving the general uh, problem of starvation in SJF and SRTN, because as the waiting time of the process becomes more, at some point of time, its response ratio will become largest, so that it will be taken for the execution. And in that way, you can prevent the starvation. Okay, you can prevent the starvation. But this prevention doesn't come free. It comes at the cost of calculating the response ratio at all instances of time. Whenever the currently running process finishes the execution, whenever currently running process finishes the execution, you need to calculate the response ratio. And when you calculate the response ratio, it will cost the overhead, and that you have to take in the picture. So if you look at the scheduling, this is how the scheduling will look like. A will be scheduled first because there is no other process. So A will execute from 0 to 3. A will execute from 0 to 3. At time t equal to 3, there is only one process, B. So B will be executed from 3 to 9. From 3 to 9, B will be executed. So B's service time, B's service time was 6. It is also executed. So now only 3 processes are remaining, C, D, and E. Right? C came at time 4, D came at time 6, and E came at time 8. And the service time is 4, 5, and 2. Right? So at this point of time, at time t equal to 9, you have to calculate the response ratio. You have to calculate the response ratio of C, D, and E. You have to calculate response ratio of C, you have to calculate response ratio of D, and response ratio of E. And out of that, whichever process has highest response ratio, whichever process has highest response ratio, that will be taken for the execution, right? That will be taken for the execution. So what is the equation for calculating the response ratio of C? So W plus S divided by S. So C came at 4. C came at 4 and current time is 9. So 9 minus 4, that is 5, plus its execution time is 4 divided by 4. So that is 9 by 4, right? C's response ratio is 9 by 4. Then the response ratio of D. So D came at 6, current time is 9, so 9 minus 6, 3, waiting time 3 plus 5 divided by 5, that is 8 by 5, right? It is 8 by 5 for D. And for E, E came at 8, so current time is 9, so its waiting time is 1 plus the service time is 2 divided by 2, right? So it is 3 by 2. So if you take this response ratios, you will see that the response ratio of C is 9 by 4, that is 2.25. Response ratio of D is 8 by 5, that is 1 by 6, and response ratio of E is 3 by 2, that is 1.5. Okay. So as per the algorithm, you can see that C's response ratio is highest, right? C's response ratio is highest. That is why C is executed from 9 to 10, 10 to 11, 11 to 12, and 12 to 13, right? 4 time units, right? So again at time t equal to 13, now you have how many processes? 2 processes, that is D and E. Now you have 2 processes, that is D and E. So again for D and E, you have to calculate the response ratio and then decide. So if you calculate the response ratio, you will see that D's response ratio is more and E's response ratio is less. So E will be taken for execution and D will be taken later on. So again, if we see the turnaround time, which is our main parameter for considering the performance. So turnaround time is 8. Average turnaround time is 8 in HRRN. SRTN was 0.20. It was 0.20. So you can see that for this set of processes, at least we can conclude that the HRRN policy is not performing well. The HRRN policy is not performing well, right? Again, as I have discussed in the previous sessions, that no policy is good or bad. It all depends on the type of example that you are taking, right? It all depends on the type of example that you are taking. Okay. So always remember that no policy is generalized good or bad. It depends on the example that you take. So this is your HRRN policy, highest response ratio next. The last scheduling policy is called feedback scheduling policy. So what is the motivation of using feedback scheduling policy. So see that if we have no indication of the relative length of the various processes, then none of the process like SPN, SRT or HRRN can be used, right? So because you see, you require this time, right? See this second column, you require the execution time. So SJF, SRTN and HRRN, they are based on calculating this expected service time of the process, right? They are basically based on calculation of the expected service time of the process. So if you don't know the service time, you only know that okay, there is a process which is coming at a certain time interval. Okay, the process is coming at certain time interval, but I don't know its running time, I don't know its execution time. Then what to do? So in that case, you can use the feedback scheduling, which is another way of establishing a preference for shorter jobs and also penalize the jobs that have been running for the long duration. So it again takes into picture two aspects. That will try to prioritize the shorter jobs, and at the same time it will try to execute the it will try to penalize the jobs that are running for the long time. So in other words, it says that if you cannot focus on the time remaining to execute, if you cannot focus on the time remaining to execute, you have to focus on the time spent in the execution so far, right? So this is another thought process that we take into picture. And if you cannot estimate the remaining time, then at least you know that for how much time the process is already executed, for how much time the process has already executed, that you already know, right? So what is feedback scheduling? So look at the layout in just a moment. So in the feedback scheduling, the scheduling is done on preemptive basis and dynamic priority mechanism, right? So if you remember round robin, right? You remember round robin. In the round robin, there was a concept of time quantum. There was a concept of time quantum. So in case of round robin, similar to round robin, the time quantum is used. Scheduling is on preemptive basis. It means that after every time quantum q, whether it is 1, 2, 3, whatever is your mechanism, it will track at certain time duration, and after that the currently running process will be preempted. Then what? When the process first enters the system, it is placed in a queue RQ0. Okay, it is placed in the ready queue, which is RQ0. After the first preemption, when it enters to the ready queue, it is placed in RQ1. Each subsequent time that it is preempted, it is demoted to the next lower priority queue. So this is a very interesting scheme you see here. So now in the traditional execution model, there is only one ready queue. In the traditional execution model, there is only one ready queue. But in case of multi-level feedback queue, there are multi-level of ready queues, right? As per the name suggests, there are multiple level of ready queue. So when the process first enters into the ready queue, into the system, is placed in RQ0. Okay, it is placed in RQ0. 0. For example, here P1. Now what will happen over the period of time? P1 will get executed for some time unit, for time unit Q. Okay. Suppose Q is 2. So for 2 seconds, it will execute. For 2 seconds, it will execute. After that, its time period is over. After that, its time period is over. So it has to again go to the ready queue and wait for its turn. Right? It has to again go to the ready queue, wait for its turn. So traditionally, it should go like this, right? But this will not happen. Instead, it will be demoted to the next queue, RQ1. It will be demoted to the next queue, RQ1. Now, why it is demoted to RQ1 and what is the meaning of demotion? It means that now its priority is less. Now its priority is less than this RQ0 queue. So now you can see, you can assume that this process P1 is here somewhere in queue R1. If any new process comes, let's say some new process P2 comes, then P2 will be entered in RQ2 again, RQ0 again. So why this discrimination? Okay, why this discrimination between P1 and P2? Because P1 has already executed for one time unit, right? P1 has already executed for one time slice. That is why it is in the waiting queue of RQ1. Now its priority is less because it has already executed for one time unit. And the process P2 has never executed. So that is why the P2 has higher priority. So next time when the scheduling is done from RQ0 first. The scheduling is done from RQ0. If there is no process in RQ0, then and then the process from RQ1 will be scheduled. Right? Now similarly, suppose P1 again executes from RQ1. P1 again executes from RQ1 at some point of time. So again it will execute for Q time units, right? Again it will execute for Q time units. So after that, what will happen? Again, when it executes for Q time units, it will be again coming back to the ready queue, but after executing from RQ1, instead of coming back to RQ1, it will go to RQ2. It will go to RQ2. One more lower priority queue. One more lower priority queue. So are you getting what is happening overall? The overall, what is happening is that new processes are always executed in RQ0. New processes are always executed in RQ0. But as the process goes older, it gets executed for the long time. It gets demoted. It gets demoted into the lower priority queues. So such feedback scheduling is called dynamic priority. Suppose this n is decided, suppose n is 3. If I say n is 3, so there are 3 queues, right? If n is 3, then there are 3 queues. So what is the problem with this approach? What is the overall problem with this approach? The problem is that when the processes are present in RQ0 and RQ, suppose this is RQ0, RQ1 and RQ2, right? Now there are certain processes present like here A, B, C, here also X, Y, Z, and here process is let's say P0, P3. Okay. So when the new process are executed, the priority queue RQ0 will be given priority. So all these processes will get executed. If RQ0 becomes empty, then and then RQ1 will be taken. So then P1, X, Y, Z, all these processes will come for execution. And only when P0 and P1, only when RQ0 and RQ1 both are empty, then and then this RQ2 will come into picture. So these processes P0 and P3 will get very less time to execute as it goes in the lower priority queue, right? So see what is happening with each execution. With each execution, the priority is getting decreased. The priority is getting decreased, right? And as it goes decreasing, it will get less time to execute, and eventually it may result into starvation. Eventually it may result into starvation. So the disadvantage with multi-level feedback queue is that the processes which are in the lower priority queues, the processes which are in the lower priority queues, they may suffer starvation. They may suffer starvation because of the less priority. Okay. So one solution to this problem is if we use the dynamic time quantum. One solution to this problem is if we use dynamic time quantum. It means that if my process is in RQ0, its time quantum will be 1, for example. If my process is in RQ1, its time quantum will be 2. If my process is in RQ2, its time quantum will be 4. So what is the advantage in that case? If the processes are executed from the lower priority queues, if the processes are executed from the lower priority queues, its time quantum will be more. So at least it will get more time to execute. It will have more time to execute, and possibly it will finish its execution because of this more time which we are giving. It will finish its execution and starvation may not happen, right? So this can be one of the solution. So this is about feedback scheduling. So if we look at the analysis of all the algorithms which is given here, this is your textbook taken. This snapshot is taken from your. In fact, this is your textbook in only. So based on various factors, the analysis is done, and we have learned these three scheduling, these six scheduling algorithms: FCFS, round robin, SJF, SRTN, HRR, and feedback. So if we talk about decision mode, you can see that 3 of them are non-preemptive and 3 of them are preemptive. Throughput is high in SJF, SRTN, and HRRN. We talk about response time. Again, response time is given here. So in FCFS, it may be high. Round robin is overall high for shorter processes. SJF having good response time for shorter processes. SRT and HRN also have good response time. So response time is basically all the scheduling algorithms are providing good response time, but overhead is one of the major concerns. So if you see in FCFS and round robin, overhead is limited, very less. Why? Because FCFS is simple policy, first come first serve, and round robin is again simple scheduling policy. One by one the processes will execute. But if you talk about all other policies like SJF, SRTN, HRR, and feedback, their overhead is more. Their overhead can be high, right? Effect on the processes like fairness, if we talk. So if you talk about fairness, HRRN is the best policy to talk about fairness policy because it takes into account all the aspects as we discussed. It takes into account all the aspects uh, of shorter processes, and also it will give preference to the processes which are waiting for the long time. So in that way, round robin can be HRRN is a good option. Next, an important consideration should be always starvation, right? So next consideration should be starvation always. So what is the effect of starvation? So there is no starvation in FCFS and round robin, right? There is no starvation in FCFS and round robin. But if you talk about SJF, there is a possibility of starvation. SRTN also there is a possibility of starvation. HRRN, there is no starvation. And finally, the feedback queue also has a possibility of starvation, right? So this is again another consideration. Talk about starvation. So you may be asked a question that, for example, which policies doesn't result into starvation, or which policy results into starvation? Why? So such kind of questions are there. You may be able to answer. You may be able to justify based on the behavior of the process. Also, you can be given a full example that certain set of processes are there, and this is the data about the process. You have to analyze with each algorithm, and with respect to turnaround time, with respect to average turnaround time, you see that which algorithm works best for this kind of processes. So that can be uh, one of the questions asked. So we can have this kind of example for this scheduling policy topic. So what I will do is in the next lecture, I will take one more example of the process scheduling algorithm, and different example I will keep it solved already, and we will see effect of each scheduling policy and which scheduling policy works good for a certain set of processes that we will analyze. So this is the end of process scheduling module. In fact, we have seen process in great detail: process introduction, PCB, process state diagram, and then process scheduling. All the scheduling policies algorithm with different analysis. So if you have any queries, we can discuss it. Otherwise, we can close the session for today. Okay, so we'll end our session. The next lecture, I will give one example of process scheduling, and then we'll move to the another topic of thread. Thread is also extension of process and a more specific form of process called thread. So we'll finish the threading topic and along with the example of process scheduling.